Okay, welcome everyone to my continuation of what are my favorite theorems. As usually, right, take it with a grain of salt, very biased point of view, my favorite theorems. Well, today's topic are Gröbner bases, and that's certainly something I would have liked to known way earlier because it's just extremely useful. So the main idea is, well, that you would like to write down kind of canonical set of generators for an ideal. Sounds pretty easy, sounds pretty simple, and it's a bit surprising that it took a while until people worked it out because it's a very natural question. So the whole idea goes back to Buchberger, who named it after his advisor, Gröbner. Okay. And it was something like 65 in his PhD thesis, roughly around the same time. A mathematician named Hironaka worked on something very similar. He called it standard bases. That name never stuck, so it's called Gröbner bases. To be completely precise, there is a much older version of Gröbner basis, which was kind of ignored in the math community, which goes back to roughly 1930, which was by a Russian mathematician called Günther, I guess. And it was basically ignored. So Buchberger discovered it, whatever it is, 50 years later. And that's the version we know today, and that's the version I'm going to talk about. So historical story time aside, what I'm basically the idea is to find kind of a minimal intersection of certain surfaces, which in the algebraic world translates to finding kind of a nice set of generators for an ideal. And I will show you a lot of Mathematica code in practice because this is very, very useful. So any reasonable computer algebra system that you would use, not just Mathematica, should have some version of Gröbner bases. And the point will be that a lot of you just need to know what it is, right? And in a lot of problems, you just want to apply it. In some sense, you don't really want to know the algorithm. The algorithm is breakfast for a computer, but a bit, well, it's not so easy to write down on paper. Anyway, it's not that bad, but it's also not that easy. But for a computer, it's breakfast, and your favorite computer algebra program should do it. And all you really, in some sense, want to know is that it exists and that you can feed it into a machine to solve your problem. And I hope to convince you that, well, it is useful. You will see. So the main idea is actually goes back to very, very old kind of mathematicians, very, very old mathematics, very classical mathematics. So you're looking for intersections of basically of varieties. So varieties are nothing else than, well, those guys. Yeah, this is a variety and this is a variety. So solutions to polynomial equations. So the zero locus of a set of polynomial equations. Here, for example, I have a red equation, which is x squared. This was a really bad square, x squared minus y squared. And I'm looking at the zero locus, and this is this red cross. If you think about it a little bit, that will be the red cross. And I have a green, which is a bit more complicated, which is x cubed minus y squared minus 1, well, equals 0, of course, again. And I can phrase this in terms of an ideal. So I'm looking at this ideal here. So the green one is, of course, this green one here. It looks a little bit like it looks a bit like a parabola. It's not a parabola, it's cubic, but it looks a little bit like it. And well, then you also have this cross. And as you can see, there are two intersections here and here. Okay, that's kind of a classical problem, and that's actually the variety I'm looking at, and this intersection. Okay, well, it looks like a reasonably classical problem. You have two very nice, well, let's say algebraic sets given by a certain number, zero locus of polynomial equation, and you ask for, well, the intersection. Turns out that you can also use this polynomial, the red one, which are just those two lines, which note is only a polynomial in y, so there is no x involved, okay? And another green one, which is this one, which is this slightly weirdish curve, which a little bit looks like this. So here it is. And it turns out that they also have two intersections, which, well, kind of look very similar to the other intersections. And indeed, they are the same. So they're the same points, which is absolutely not obvious if you just look at and if you like just look at the pictures, you might be convinced that they are the same points, but it's not quite obvious why they should be the same points, right? In other words, I'm looking for a solution to this set of equations, and I'm looking to the solution to this set of equations, and I kind of claim that they are the same. In other words, I kind of claim that the two ideals spent by those two polynomials are the same. And I don't know how you feel. Look at the polynomials, right? That doesn't look, here's the degree 6 polynomial in y, here's the degree 3 polynomial in x. There is no corresponding thing on the other side. A priori, I don't see any good reasons why they should be the same. And this whole idea of Gröbner bases is to determine, to provide an algorithm to check whether this question mark here is actually true or not, right? So you have two ideals, and you want to check whether they are the same. And Gröbner's idea, Gröbner's algorithm, also Buchberger's algorithm, actually describing Gröbner bases, provides you an algorithm to do that. And as I said, it's actually really practical in the sense that any reasonable computer algebra system should have some version of it implemented. And if you just look at this question, this looks, as I said, very classical, right? You have a system of polynomial equations and you want to solve them. And I will show you later, actually, that the Buchberger algorithm, so computing Gröbner bases, gives you a way to do that. So whenever, that's kind of the takeaway message of this video. So whenever you have some polynomial system of polynomial equations you need to solve, and that happens all the time, of course, because we are talking about polynomial equations, try some Gröbner algorithm, try some Gröbner argument. That actually might work. Yeah, so let me describe a little bit this Buchberger algorithm. I don't want you to know all the details. Well, I would be, well, so the details are linked in the description if you want to read the details, of course. But kind of the philosophy is that I would like to leave the details to, well, either the interested reader or even better to a computer, because in the end it's an algorithm, and it's not a bad algorithm. It's pretty easy to implement. It runs reasonably fast, and well, you just need to know that it exists. You feed it into a machine, it spits out a result. Basically, that's the idea. It's not quite true. Sometimes you want to do it by hand, or sometimes you want to do it more general, and that's why, as I said, I link the formal description in the formal definition in the description. And yeah, it's not that bad. And maybe you need 2 or 3 pages to actually write it down precisely. Anyway, there's one crucial ingredient, which is always very confusing, and I will show it to you in a Mathematica demonstration in a second, which is very crucial. It's very easy, and everything depends on it. So actually, it's not just one algorithm. There's an algorithm with a choice involved. And the usual choice involved is some ordering you need to choose. And it's so important that I spent one whole slide just to talk about this ordering. So standard ordering would be something like you say, I like x. So let's say you have 3 coordinates, x, y, z, of course, x1, x2, x3 if you want. And you need to choose some ordering on them. That would be something you could do. Let's say I like x better than y, better than z. And then you have your given polynomial. This is some crazy polynomial, whatever it is, in x, y, z, and you need to order it according to this order. And it's a very easy idea. It works as follows. So you first order everything according to x. So highest powers of x first. Well, there is no x cubed. So x to the 4th is the first one. There's no x cubed. Then there's an x squared somewhere in this expression here. So where's x squared? Here's x squared. So this is the second one. This is the first one. Then you look for the next one, x1. Let's see. Here's an x. Here's an x. And here's an x, so you order them, you all put them together, and everything else without an x. Here's no x, here's no x, here's no x, here's no x. So x to the 0, you again order them. And that's your order according to x. So you just order everything according to the powers of x. And then you look at whatever remains in the brackets. Well, maybe I shouldn't use yellow. Whatever remains in the brackets, right? So those bracketed terms. And you order the bracketed terms as well. So maybe let's have a look at the last one. So for all x to the 0 terms, these are those ones here, the purple, whatever it is, purple ones. For all x to the 0 terms, I have 6 of them. I have already ordered everything according to x, and x was my favorite. So I look at my second favorite, which is y. So in this example, y is my second favorite. So I order everything according to y. Right? Same procedure. I order everything according to y. I look what remains, and then I order everything according to my last one, which is z. I order everything according to z, which gives me a total order on the coefficients of the polynomial by just reading from bottom to top. And that's how I would read them. So this is the leading coefficient, the leading term, LT, in this order, with respect to x, and so on, right? So you just order it according to a certain order that you use. Right? X comes first, let's say, then y, then z. Order everything according to x. You see well, x might appear several, x might have, x to the one might have several terms associated to it. Then you order the whatever it remains in the bracket according to y, whatever remains in the bracket, order it according to z, whatever remains in the bracket, order it according to x4, something like that, right? So very easy, and it's called kind of the monomial order of this polynomial. And you can do this for any polynomial. And you have the notion of a leading term. And everything will depend on this choice of order. So as usual trick, if you want to solve a polynomial equation, is you can play around with those orders, and you might get actually easier results. So this is actually not a flaw in some sense. This is a feature of the theory. Play with all orders. For example, I could have also chosen y before x or something like that. Play with those orders, and you might get nicer solutions. Again, a Mathematica demonstration will follow in a second. And then you have this Buchberger algorithm. And I said again, it's a bit confusing. So Buchberger actually was the one who worked on Gröbner bases, and he named it after his advisor. So it's not called Buchberger bases, it's called Gröbner bases, because he, as I said, named it after his advisor. But Buchberger was a main name. Together with the other two, which are a little bit ignored, or were a little bit ignored by the math community, the Hiroka one, that called Think Standard Basis, and the old Russian one from 1930, Günther, which was kind of ignored for something like 70 years. Some links are in the description. Anyway, it's a very, very simple algorithm, actually. And I will show it to you in practice in a second, or in a Mathematica demonstration. Basically, you start with an ideal given by a certain number of elements, h1 up to hs, and you want to construct the Gröbner bases, g1 up to gt. So t doesn't need to be s, right? It actually can vary. And the way you do it is you just run through all elements. You have this funny s polynomial, which is a certain expression which I don't want you to look at too closely. This is breakfast. This is kind of a polynomial minus a polynomial. This is breakfast for a computer. Not so hard. And then you do some division algorithm on this polynomial, and whenever you get something non-zero, you actually include it in your set, and you do this until you can't include anything anymore, right? So while g is not g prime, do blah, 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 and in any step you check whether you have a new element that you can add, and then you set g gets bigger and bigger and bigger, and then you just run the algorithm until it stops. And by something like Hilbert's basis theorem, you actually know that this algorithm will eventually terminate. So let's have a look at the very easy Mathematica demonstration, which is also linked in the description. So here's the algorithm, and as you can see, you can play around with the order. In this example, it doesn't change anything, but we can have a new example, Oh, this is a big example. And as you can see, the output depends on my chosen ordering. And this is a very nice example. So let's just do it. So with new example, I basically get a new random set. So you start with certain polynomials in x and y. So you have only two ones. Here you compute this s polynomial. It gives you something. You compute the remainder using this s polynomial. You get, so this is a polynomial division. It's if you know how to do polynomial division, you basically know how to do this one. This one is straightforward. The formula was actually on my slide that you have seen before, and that you will see in a second again. It's not so important. You could just do it. It's a really easy calculation. Anyway, so you compute this s polynomial, you compute a remainder, you do some polynomial division, you get this funny thing, minus 2y cubed and whatever, and you realize, oops, that's not 0, so you include it into your bigger set. So G still has the old polynomials, and now you get a new one. Okay, and then you continue that procedure. Now you need to compute two S polynomials, namely the mixed ones. This, the first one with the last one, the second one with the last one. You get new expressions. You do division algorithm. In this case, you get 0 twice. So this thing then stabilizes and everything is fine, right? So if you go ahead, the set is stabilized and everything is fine. And that's then your Gröbner basis for the ideal. And this really depends on the order. If I choose a different order, then I give a different basis. If I choose a different order, I get a different basis. Right, so here I have something like x squared over 2 plus whatever. And here I have minus 7y squared over 6 plus whatever. Okay, so let's do another one just to get started, just to get the feeling. So you start with a certain polynomial, with two certain polynomials. You do this S polynomial for all things you see in G, so for all pairs you can form. You get something, you do a polynomial division, you see something new, you put it into your set, and you repeat. So now you have three elements in your set. You need to do two S polynomials, first one with a new one, second one with a new one. You check the remainder, and again, in this case, you again get 0 as a remainder, so you don't add anything. So in this step, you're done. And this is your Gröbner basis. And again, oh, in this case, actually, you're lucky, and it doesn't depend on the different order. Anyway, you can play around with this a little bit. Just press new example. Well, this one is also very nice. So let's do this one. So you have those two polynomials. You do the S polynomials. You do the remainder. You get 6. You put 6 into your basis. You do the same again. You do two S polynomials. You get division 0, and that's it. You're done. And because 6 is in your basis, of course, the Gröbner basis itself is trivial. Right? But if an invertible element is in your ideal, then the ideal is a trivial ideal, meaning it is so the ideal is the whole ring. Yeah, so that's actually a funny demonstration that is linked below that you can play around a little bit if you really want to understand the details of the algorithm. As I said, the algorithm isn't all that bad. You have this S polynomial you need to compute. You need to reduce everything, and you add new elements as long as they are not 0. And at one point it will stabilize because all new kind of polynomials you could add are at 1.0. And whatever you get out is then the Gröbner basis G. And the point is, yeah, that's exactly what's going on. So it is a Gröbner basis, and the Gröbner basis has those two properties. So that's also a reduced version. It isn't so important, but basically the point is this algorithm constructs Gröbner bases for you. So if you look at the description, if you look at the formal definition, it's not quite clear why they should exist, but this Buchberger's algorithm construct them for you. And I said again, basically any computer algebra program should be able to run some version of Buchberger's algorithm. Just Google Gröbner and your favorite computer algebra system, might it be Mathematica or Sage or Magma or whatever you like to use. Should be able to run this algorithm which constructs the Gröbner basis for you. And up to this certain choice, what do you call reduced? Well, everything is, by the way, with a fixed order. So I already have a fixed order. For any fixed order, I get existence. And if I kind of only allow certain type of Gröbner bases, there's, of course, a choice, because you think of it like a basis of a vector space, right? There's a certain choice. You might need to normalize it. You call it reduced. And if it's reduced, it's unique. And that's very nice, because now it characterizes ideals uniquely, which means if you want to check whether two ideals are the same, just run the Gröbner algorithm or the Buchberger algorithm on both. If you get the same result, then they are the same. If you don't get the same result, then they're not the same. So it characterizes of existence and uniqueness exactly the statement you would like to see. Because this video already gets too long, I decided not to talk too much about applications. Some link is in the description. But of course, this is super useful outside of ring theory, outside of abstract ring theory, because you basically calculate bases for ideals, right? So there are applications in computer sciences, in graph theory, in theorem proving, and a lot more. Or maybe more down to earth and coming back to where we started. So Gröbner theory or Buchberger's algorithm, whatever, as I said, works for any computer algebra system. Here's my Mathematica code. It's really simple. It's just one line, basically. And it helps you to solve polynomial equations. And yes, of course, that is applicable everywhere, right? Polynomial equations. We are talking about polynomials here. So let's have a look at this example. So I have two polynomials, a red one, which is this little curve here. So it's this polynomial. And I have a green one, which is this strange curve here, this polynomial. And I kind of want to solve this polynomial equation. And I look at the picture and I kind of see they seem to intersect in just one point. But look at the polynomials. It's cubic in y, quadratic in x. Maybe not super easy to solve. Okay, so what I do is I want to solve it. I feed it into Mathematica. Here's just the code. It's very simple. You can feed in any number of polynomials, in any number of variables. In this example, of course, two polynomials and two variables. You choose an order, which is the second thing is this choice of order. And the result is a Gröbner basis. So here's a Gröbner basis. And this is a plot of the Gröbner basis. So again, it has a red polynomial, which is just a stupid line here. And it has a green polynomial, which is this parabola-like thing that goes all the way to here. And the point is, of course, that existence and uniqueness, so ideals are usually are uniquely determined by the Gröbner basis. So I know that the point I was looking for originally is just this intersection point. So instead of solving this set of polynomial equations, which I really don't know how to do a priori, it has a y cubed, it has an x squared, it has xy, I don't really know what to do here. I just translated using Gröbner theory into a much, much simpler system of equations. So this one, for example, only involves y, right? It's a polynomial just in y, which is definitely much easier than a polynomial in xy. Also, the degree is higher, the degree is 5, but still, it's only a polynomial in y. So in the worst case, you could try to solve that just numerically. In this example, actually, you only get one real solution. That's why this polynomial looks just like this line here, just one real solution. And then this is extremely easy. The other one is then extremely easy to solve because then you only need to solve it for a fixed y, right? And for a fixed y, this is degree 1 polynomial in x. And that's trivial to solve. So actually, this set of equations, it's just much easier to, so the red one is much easier to solve than the blue one. And the only thing I did is I transformed the blue one into the red one using, well, this very simple line in Mathematica. And that's it. I could have actually done that by hand. So, but again, the only idea I would have to do this by hand instead of just feeding it into a machine would be to run Buchberger's algorithm and to construct the Gröbner basis and then just solve it. Okay, to wrap up, so Gröbner basis, Buchberger's algorithm is an idea to just write down a nice set of generators for an ideal, which nailed down the ideal up to a certain choice of normalization, which is very powerful. So for two reasons. First of all, the algorithm is pretty simple. You could feed it into a machine, you can just ask the machine. The second is, of course, we are talking here about solving systems of polynomial equations. So yes, that is important, and this will turn up everywhere. So the idea is, if you have a system of polynomial equations, you don't know what to do, like you have something with an x cubed and something with a y to the whatever, and maybe a z somewhere around, just feed it into the Gröbner machine, see what comes out. In a lot of cases, it's just much easier to solve a much easier equation. By uniqueness, you know that solving the much easier equation also solves your original problem. Anyway, I hope you enjoyed the video, and I also hope to see you next time.